Today's honors geometry lesson is on square roots and radicals. The objectives are to simplify radicals and to rationalize the denominator to simplify radicals. A number x is the square root of a real number b if and only if x squared is equal to b. A square root of a number is one of two equal factors of that number. This symbol here is called the radical sign, and the number underneath the radical sign is known as the radicand. We are going to practice and review some of the perfect squares with square roots. So from previous knowledge, we know that a square root is a number times itself, and we're looking for our perfect squares. So the square root of 64 is 8, because 8 times 8 is 64. Square root of 49 is 7, so 7 times 7 is 49. The next one, square root of 16 is 4, because 4 times 4 is 16. The square root of 1 is 1, since 1 times 1 is 1. And the square root of 169 is 13, since 13 times 13 is 169. At this time, go ahead and stop the video. Practice the rest of the square roots, your perfect squares, and when you're ready to check your answers, go ahead and start the video. So here are the answers to the rest of the square roots of perfect squares. So go ahead, again, stop the video, check over your work, and when you're ready to move on, start the video. If an integer is not a perfect square, the square root of the integer is irrational. It cannot be written as either a terminating or a repeating decimal. So radical 3 is an example. Such roots can only be approximated using decimal numbers. When asked to find exact answers, you will write the radical form rather than the decimal approximation. So when simplifying radicals, we are going to simplify radicals by removing the factors of a perfect square from underneath the radical sign. This requires a use of what we call the product property of radicals. So the product property of radicals allows us to take the factors of a number underneath the radicand and break it up into two different radicals. So an example is root 15. So root 15 can be broken up into root 5 times root 3, since 5 times 3 gives us 15. The property also works backwards, where if you have two roots, so here we have root 5 times root 11, we can multiply the numbers underneath the radical sign. So 5 times 11 is 55. And we can go ahead and turn that into one root, or root 55. So same thing for the third example. So we know that root 21 has the factors of 3 and 7, so we can rewrite this as root 3 times root 7. Now 4 is a special case. So if we look at 18, 18 does have several factors that multiply to 18. So we have 2 times 9, and we have 6 times 3. When simplifying radicals, you want to make sure that you've taken out all the factors of a perfect square from underneath that radical sign. So if it helps, go ahead and as you simplify, write your perfect square. So we have perfect square of 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. So what we're looking for is we're looking to see if there is a perfect square contained in a factor of 18. And what we know is that that's going to be 9. So we can rewrite this as root 9 times root 2. And we can go one step further and say, well, root 9 simplifies to 3. So we have 3 times root 2. And 3 times root 2 is the same thing as just 3 root 2. So now we have simplified this radical in our exact answer. So the one rule that you need to remember about simplifying radicals is you can leave no perfect square factors underneath that radical sign. So let's take a look at a few examples. So again, if you have to write your perfect squares on the bottom of the screen, go ahead and stop the video and do so at this point. So if we look at root 8, we know that root 8 has a perfect square factor of 4, and 4 times 2 also gives me 8. So I'm going to simplify root 4 into 2. So our simplified exact answer is 2 root 2. For example 5, root 20. So again, I know root 20 has different factors. We can have 2 times 10, but 2 and 10 are not perfect squares, so we want to look for other factors of 20 that does contain a perfect square. And we know that that is going to be 4 times 5. So the square root of 4 is 2, so this simplifies into 2 root 5. For example 6, we have root 98. So this is where it comes in handy to write your perfect squares on the bottom of the screen. So if we go ahead and quickly do this, so 1, 4, 9, 16, 25, 36, 49, 64, 81, and then we can have 100. Okay, so we're looking for factors of 98 that also contain a perfect square, and that's going to be this right here. So we know that 98 does give me 49 times 2, so the square root of 49 is 7, so our simplified answer is 7 root 2. So at this time, I would like you to stop the video, work on examples 7 through 10, and when you're ready to check the answers, go ahead and start the video again. So here are the answers for examples 7 through 10. For example 11, we have two radicals that are being multiplied by each other. Sometimes it's easier to simplify each radical first, meaning that there are no perfect square factors underneath the radical, and then multiply those simplified radicals. So here we have root 8. So we know from example 4 that root 8 is the same thing as 2 root 2. Root 20 from example 5 is the same as 2 root 5. When multiplying simplified radicals, you may only multiply numbers outside the radical with another number outside the radical. So we're going to take 2 times 2, which is 4. And you can only multiply numbers underneath a radical with another number underneath the radical. So here we have root 2 times root 5, which is root 10. And here is our simplified radical. Now what you want to do is sometimes when you multiply, the number underneath the radical may not have contained a perfect square when you first started, but as you simplify, it may turn into a radical that can still be simplified further. So if we take a look at example 12, here's a perfect example of that. So if we look at root 5, we know there are no perfect squares in root 5. If we look at root 15, we can also see there are no perfect squares in root 15. So we're going to go ahead and multiply like we did in example 11. So 3 times 2 is 6. Root 5 times root 15 is actually root 75. So if we go back down to our perfect squares, we can see that 25 is a perfect square that is contained underneath the radical sign as a factor of 75. So we know that the square root of 75 is also the same as root 25 times root 3. Go ahead and change this so we can see the color. Okay, so now if we keep this 6, we know the square root of 25 is 5. And then just like before, if there is a number outside a radical times another number outside the radical, we can simplify those. So 6 times 5 is 30. So our simplified answer is 30 root 3. When simplifying radicals, sometimes it may have to do what's called rationalizing the denominator. And what this means for our second rule is we can have no radicals in the denominator of a fraction. So if a fraction has a simplified radical in the denominator, we're going to simply multiply the numerator and denominator of the fraction by that radical. And again, this process is called rationalizing the denominator, which allows us to remove the radical from the denominator but does not change the value of the overall fraction. So for example 13, we have 2 divided by root 3. So when we rationalize the denominator, we're going to take the simplified denominator and multiply that by both the numerator and the denominator. Okay, So we have 2 times root 3, which is 2 root 3. And then on the bottom, we have root 3 times root 3, which is root 9. So what rationalizing the denominator is going to do is turn that bottom number into a perfect square. So we know that 2 root 3 is simplified because 3 does not contain a perfect square, but we do know that the square root of 9 is 3. So now we have our simplified fraction of 2 root 3 over 3. For example 14, we happen to have a radical in the numerator and a radical in the denominator. So same process, root 7 is already simplified. So to go ahead and rationalize that denominator, we're going to multiply the numerator and denominator by root 7. Okay, so root 5 times root 7 is root 35. And then root 7 times root 7 is root 49. And we know that the square root of 49 is 7. So let's go ahead and take a look at 15. So we have root 10 over root 2. So as it is now, root 2 is simplified. So to get rid of that radical in the bottom, we're going to multiply the numerator and denominator by root 2. So root 10 times root 2 is root 20. And root 2 times root 2 is root 4. So when you multiply, remember we said sometimes the radicals by themselves do not contain perfect squares, but when you multiply them, they do. And here's an example. So we know from the previous slide that root 20 does contain the square root, or the perfect square of 4. So we know that 4 times 5 is 20. So when we simplify this, it simplifies into 2 root 5. And we know that 4 is a perfect square, which simplifies to 2. Now, just like simplifying fractions, and just like multiplying fractions or radicals, you can simplify numbers outside the radical with another number outside the radical. So we know that 2 root 5 over 2 is going to simplify to root 5. So for the last example, 16, we have 2 over 5 root 3. So remember, it is okay to have numbers in the denominator without a radical, but we have to get rid of that radical. So for this one, we are only going to multiply by the number under the radical, which is root 3. So 2 times root 3 is 2 root 3. We have the 5 underneath the radical, but we're going to take root 3 times root 3, which is root 9. And we're going to keep continuing and simplify. So 2 root 3 is simplified. I want you to watch what happens here. So I'm going to bring over the 5. Remember, you're actually multiplying 5 times root 9. So when we simplify root 9, that is going to give us 3. So when we simplify the bottom even further, we're going to get 2 root 3 over 15. Lastly, for this lesson, we're going to talk about the quotient property of radicals. So just like multiplication, if you have a number underneath a radical, you can break it up into its 2 factors. So let's say we review. So if we have root 50, remember we can break that up into root 25 times root 2. This is very similar to the quotient property of radicals as well. So if you have 2 numbers underneath a radical sign as a fraction, you can go ahead and turn both the numerator and denominator into their own radical, and then from there we can simplify. So for example 17, we have root 10 over 9. So what this allows us to do using the quotient property is rename this as root 10 over root 9, and then it allows us to simplify like we learned on the last slide. So root 10 does not contain a perfect square, and I'm going to go ahead and just make this bigger so we can see. That's already simplified, but we know that the square root of 9 is 3. So this property just allows us to simplify down to the smallest root. So for 18, we're going to go ahead and do the same thing. So we're going to go and turn this into root 18 over root 25, and then we're going to start simplifying. So root 18 contains a perfect square of 9, and then 9 times 2 is 18. And the square root of 25 is 5. So let's go ahead and simplify that perfect square. So the square root of 9 is 3. So our simplified answer gives us 3 root 2 over 5. So this leads us into our last simplified radical rule, which says we can have no fractions underneath a radical. So if there is a simplified fraction under a radical, we're going to split the fraction into two radicals, make it a radical over a radical, and then we're going to use what we know about rationalizing the denominator. So for example, 19, we have a radical 1 over 9, or root 1 over 9. We're going to turn this into root 1 over root 2. And then we're going to go ahead and rationalize the denominator. So since 2 is already a simplified radical, we're going to take root 2 and multiply that by the numerator and the denominator. Okay, so root 1 times root 2 is root 2. And root 2 times root 2 is root 4, and the square root of 4 is 2. And there we have our simplified answer. So for 20, I'm going to go ahead and do the same thing. So the first thing we're going to do is break this up into root 15 divided by root 18. So remember from the previous slide, we want to make sure that the denominator is simplified. Okay, so we can't simplify root 15. There are no perfect squares. But root 18 is the same thing as root 9 times root 2. So the square root of 9 is 3. And so this simplifies into 3 root 2. So then from here, remember, we're only going to multiply the numerator and denominator by the radical. So we're going to do root 2 over root 2. And then root 15 times root 2 is root 30. And then here, we have 3. And then root 2 times root 2 is root 4. And we know that the square root of 4 is 2, so 3 times 2 gives us 6. And remember, you always want to make sure that there still are no perfect squares contained underneath a radical. So if we look at root 30, there are no perfect squares in root 30, so therefore, we are simplified. So this is the end of our lesson today on radicals. If you have any questions, feel free to watch the video for a second time. And as always, if you still have questions, bring those questions into class tomorrow, where we'll be working on a radical worksheet to review all the different rules for simplifying radicals.